When we begin discussing why intelligent life may be unlikely, we must start with the scale of the universe itself. At first glance, the vastness of the cosmos seems to argue the opposite conclusion. If the universe is so enormous, containing unimaginable numbers of stars and planets, then surely intelligent life must be common. That is the intuitive reaction most people have. However, the deeper we explore the true meaning of vastness, the more we realize that size alone does not guarantee abundance. In fact, it may highlight how rare certain outcomes can remain. To understand this properly, we must first grasp just how large the universe truly is. The Earth feels big to us. It has oceans, continents, mountains, and billions of people. Yet compared to the Sun, Earth is tiny. You could fit over 1 million Earths inside the Sun, and the Sun itself is just an ordinary star. Not the largest, not the brightest, not even particularly special in cosmic terms. Our Sun is one star among roughly 100 to 400 billion stars in our galaxy, the Milky Way. That number alone is staggering. If you tried to count one star per second, it would take thousands of years to finish counting them all. And the Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Each galaxy contains billions or even trillions of stars. When you multiply these numbers together, you begin to approach figures so large that the human mind struggles to comprehend them. At this point, many people conclude that intelligent life must be inevitable. With so many stars, there must be countless planets. With countless planets, there must be countless Earth-like worlds. And with countless Earth-like worlds, there must be countless civilizations. But this line of reasoning makes an important mistake. It assumes that probability scales directly with quantity. It assumes that if you have enough trials, a rare event becomes common. That is sometimes true, but only if the event is not astronomically rare. Consider a simple analogy. Imagine a vast desert stretching for thousands of miles. In that desert, there are trillions of grains of sand. Now, suppose that only one grain in a trillion is made of pure gold. Even though the desert contains enormous amounts of sand, the gold remains incredibly rare. You might search your entire life and never find a single golden grain. The desert's size does not make gold common. It merely means there is more sand. The universe may function in a similar way. It may be filled with stars and planets, yet the specific combination of conditions required for intelligent life might be extraordinarily uncommon. Vastness does not automatically translate to abundance of complexity. Another key factor is distance. The stars are not only numerous, they are separated by immense emptiness. The nearest star to our solar system, Proxima Centauri, is about 4.24 light years away. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. That means even our closest stellar neighbor is tens of trillions of kilometers away. If you could travel at the speed of our fastest spacecraft, it would take tens of thousands of years to reach it. This immense separation matters. Even if intelligent civilizations exist elsewhere, the distances between stars make communication and interaction extremely difficult. Signals weaken over distance. Space travel requires unimaginable energy. The universe is not only vast in number, it is vast in emptiness. Most of it is cold, dark vacuum. The observable universe is about 93 billion light years in diameter. That number is almost impossible to visualize. If the entire history of human civilization were compressed into 1 second, the age of the universe would still span many years in comparison. We exist in a tiny slice of cosmic time and space. Now, here is where Richard Feynman's perspective becomes important. Feynman emphasized intellectual honesty and caution in scientific reasoning. He warned against being fooled by our intuitions. Large numbers impress us. They give a sense of inevitability. But mathematics teaches us something subtle. Even in enormous systems, certain outcomes can remain extremely rare. If the probability of intelligent life emerging on any given suitable planet were 1 in a billion, then even billions of planets might produce only a handful of intelligent civilizations. If the probability were 1 in a trillion, intelligent life could be effectively unique within our observable universe. Without knowing the true probability, we cannot assume abundance. The vastness of the universe also stretches across time. The universe is approximately 13.8 billion years old. Our solar system formed about 4.6 billion years ago. Complex life on Earth has existed for only a few 100 million years. Human technological civilization is only a few thousand years old, a blink of an eye in cosmic terms. This means that intelligent life may not only be rare in space, but also rare in time. Civilizations may rise and fall. They may exist for only brief periods before disappearing. 2. Civilizations could exist in the same galaxy yet never overlap in time. The vast timeline of the cosmos reduces the likelihood of simultaneous contact. Furthermore, most stars in the universe are not like our sun. Many are red dwarfs, smaller and cooler. Others are massive stars that burn brightly but live short lives, exploding as supernovae after only a few million years. Planetary systems can be unstable. Some planets are gas giants with no solid surface. Others are tidally locked with one side permanently facing their star. The variety of cosmic environments is immense, but suitability for life may be narrow. The vastness of the universe also means we observe only a fraction of it. The observable universe is limited by the speed of light. There may be regions beyond our observational horizon that we will never see, but even within what we can see, the scale is overwhelming. And yet, despite decades of searching, we have found no confirmed evidence of intelligent extraterrestrial life, no clear signals, no artifacts, no spacecraft. This silence is striking when compared to the universe's size. If intelligent life were common, we might expect at least some detectable traces. The vastness of the universe therefore presents a paradox. On one hand, it seems to increase the chances of life. On the other hand, its enormous scale emphasizes how small and isolated we may be. It reminds us that rare events can remain rare, even in a cosmos filled with stars. Feynman would likely remind us not to jump to comforting conclusions. Science does not operate on hope or imagination. It operates on evidence. The sheer size of the universe is not evidence of abundant intelligence. It is simply a measurement of scale. When we truly confront the vastness of the universe, we experience a humbling realization. Earth is a tiny planet orbiting an ordinary star in one galaxy among trillions. Our entire history occupies a microscopic fraction of cosmic time. The universe does not appear structured around us. It does not show obvious signs of widespread intelligence. This does not mean we are alone. It means we do not know. And until we know, the vastness of the universe remains both inspiring and sobering. It inspires because it reveals grandeur beyond imagination. It sobers because it suggests that even in such grandeur, intelligent life may be astonishingly rare. The scale of the cosmos challenges our assumptions. It forces us to replace emotional intuition with mathematical reasoning. And when we do, we realize that vastness is not a guarantee. It is simply a backdrop, an immense stage upon which rare events may unfold only occasionally. Understanding this is the first step in examining why intelligent life may be unlikely. The universe is unimaginably large, but rarity can persist even within infinity-like scales. And that possibility, that we may be one of very few conscious observers in a vast silent cosmos, is both unsettling and profoundly meaningful. When we continue exploring the vastness of the universe, we must go deeper than just counting stars and galaxies. Vastness is not only about how many objects exist, it is also about how space behaves, how matter is distributed, and how the universe evolves over time. When examined carefully, the cosmos reveals not a crowded arena full of thriving civilizations, but an overwhelming ocean of emptiness, punctuated by isolated islands of matter. Most of the universe is vacuum. If you removed all stars, planets, gas, and dust, what would remain is an almost perfect emptiness, stretching in every direction. Even within galaxies, stars are separated by enormous distances, If the sun were the size of a marble placed in a large city square, the nearest star would be another marble placed hundreds of kilometers away. That comparison shows how sparse the universe truly is. This sparseness matters because interactions are rare. For intelligent life to arise and then spread, conditions must not only be right locally, but connectivity must be possible across cosmic distances. Yet space expansion complicates everything. The universe is not static, it is expanding. Galaxies are moving away from each other, and the farther they are, the faster they recede. This expansion means that over time, large portions of the universe become permanently unreachable. Even light emitted today from distant galaxies may never reach us if space expands quickly enough. So vastness is not just size, it is dynamic separation. When we look at the cosmic web, the large-scale structure of the universe, we see that matter forms clusters and filaments separated by enormous voids. These voids can span hundreds of millions of light years. Imagine entire regions of space where almost nothing exists. In such a structure, even if intelligent life arises in one cluster, it may be forever isolated from life in another cluster. Another crucial point is statistical misunderstanding. Human intuition is not well adapted to extremely large numbers. We evolved to deal with small quantities, dozens, hundreds, maybe thousands. But the universe operates with numbers, in the trillions upon trillions. When people hear that there are billions of potentially habitable planets, they assume intelligence must be common. Yet we do not know the probability of life forming. If that probability is extraordinarily small, for example, 1 in 10 circumflex 20, then even billions of planets would not be enough. This is where careful reasoning becomes essential. Richard Feynman emphasized that science requires us to question assumptions, especially those that feel comforting. It feels comforting to believe we are part of a bustling cosmic community. It feels less comforting to imagine we may be alone. But feelings are not evidence. The vastness of the universe also magnifies the role of chance. In a small system, patterns may dominate. In a vast system, randomness can create wide variation. Planets form in chaotic environments. Asteroid impacts occur unpredictably. Supernova explosions can sterilize nearby systems. Gamma ray bursts can flood entire regions with radiation. The larger the universe, the more opportunities there are for catastrophic events that prevent life from developing or surviving long enough to become intelligent. Time adds another layer of vastness. The universe will likely exist for trillions of years into the future. Stars like our Sun are relatively short-lived compared to red dwarf stars, which can burn for trillions of years. This means that most potential life-bearing opportunities may lie far in the future, not the present. Humanity may be early, not late, in cosmic history. If intelligent life tends to arise around long-lived stars, then perhaps the universe is still in its early biological phase. But again, this possibility highlights uncertainty, not abundance. Consider also that the observable universe may be only a small fraction of the total universe. Cosmological theories suggest space could extend far beyond what we can see, possibly infinitely. However, even if infinite space exists, we are limited to what we can observe and interact with. Regions beyond our cosmic horizon are causally disconnected from us. For all practical purposes, they do not influence our existence. So, when discussing intelligent life, we must focus on the observable region. And within that region, evidence remains absent. Another important aspect of vastness is energy distribution. The universe is dominated not by stars and planets, but by dark energy and dark matter, or binary matter, the kind that forms atoms, planets, and living organisms, makes up only a small percentage of the total cosmic content. The majority of the universe consists of components that do not form life as we understand it. So while the universe is vast, the fraction that can even potentially support chemistry is limited. Even within galaxies, only certain regions are suitable for stable planetary systems. Areas too close to the galactic center experience intense radiation and gravitational disturbances. Areas too far out may lack heavy elements necessary for planet formation. This creates what some scientists call a galactic habitable zone. So the vastness of a galaxy does not mean all of it is equally promising for life. Let us also consider the psychological effect of vastness. When humans first realized how large the universe is, it changed our sense of importance. Earth was no longer the center of everything. We became a small part of a grand cosmic structure. This realization can lead to two opposite reactions. One reaction is humility. We are small and possibly alone. The other reaction is optimism. Because there is so much space, there must be others like us. But neither reaction is automatically correct. They are emotional interpretations of scale. Science demands something different. It demands evidence and probability analysis. The vastness of the universe also complicates detection. Our radio signals have only traveled about 100 light years into space, a tiny bubble compared to the size of our galaxy, which spans about 100,000 light years. That means even if civilizations exist elsewhere in the Milky Way, they may not yet know about us. Similarly, their signals may not have reached us. Vastness slows communication to cosmic timescales. However, even with this limitation, we might expect to see indirect signs, large-scale engineering, unusual energy signatures, or anomalies in stellar behavior. So far, we have not observed confirmed evidence of such phenomena. The silence persists. One might argue that vastness increases the odds that somewhere, sometime, intelligent life has existed. That may be true. But the key question is frequency. Is intelligent life common enough that galaxies are filled with civilizations, or is it so rare that even in billions of galaxies only a handful ever emerge? The vastness of the universe does not answer this question. Instead, it frames it. Imagine flipping a coin. If the coin is fair, half the flips will be heads. But imagine a coin that lands on heads only once every trillion flips. Even if you flip it billions of times, you may never see heads. The universe may be flipping a rare coin when it attempts to produce intelligent life. Another sobering thought is entropy. The universe trends toward disorder. Stars burn out. Energy spreads thin. Over extremely long timescales, usable energy decreases. Intelligent civilizations require energy to survive. Vastness includes not just space, but thermodynamic decline. In the distant future, the universe may become dark and cold, limiting the window during which intelligence can exist. So when we fully examine the vastness of the universe, we see something profound. Yes, it contains enormous numbers of stars and planets. Yes, it spans billions of light years and billions of years. But it is also mostly empty, mostly dark, mostly inhospitable, and governed by physical laws that do not guarantee complexity. The true lesson of vastness is not inevitability, it is perspective. We are a small phenomenon in an immense system. Rare outcomes can remain rare even when the stage is enormous. Large numbers can still yield small results if probabilities are tiny. Richard Feynman's intellectual discipline would encourage us to hold two ideas at once. First, we should be open to the possibility that life exists elsewhere. Second, we should not assume it does, simply because the universe is large. The vastness of the cosmos is awe-inspiring, but awe is not evidence. In the end, the vastness of the universe makes our existence either common or extraordinarily special. If intelligent life is rare, then we may be one of very few conscious witnesses to this immense reality. If it is common, then one day we may discover others. But until that discovery is made, the vastness of the universe remains a silent backdrop, magnificent, mysterious, and possibly sparsely populated by minds capable of understanding it. And that silence, stretched across billions of light years, is what forces us to consider seriously the possibility that intelligent life is not just uncommon. It may be one of the rarest outcomes the universe ever produces. When we move from the vastness of the universe to the rarity of stable conditions, we shift from quantity to quality. The universe may contain countless stars and planets, but the question is not how many worlds exist. The real question is how many of those worlds remain stable long enough and under the right circumstances for life to emerge and evolve into intelligence. Stability is the key word. Life does not merely require the right ingredients, it requires the right conditions sustained over immense stretches of time. Even small disturbances can prevent life from forming or wipe it out before it becomes complex. When we carefully examine what Earth needed in order to produce intelligent life, we begin to see how delicate and unusual those stable conditions might be. Let us begin with the most obvious factor: distance from a star. Earth orbits the Sun at a distance that allows liquid water to exist on its surface. If Earth were significantly closer, temperatures would rise, oceans would evaporate, and a runaway greenhouse effect could occur, similar to what happened on Venus. If Earth were significantly farther away, water would freeze and the planet could resemble Mars, cold, dry, and barren. This region where liquid water can exist is often called the habitable zone. However, being inside the habitable zone is not enough. Venus and Mars are often described as being near or within the Sun's habitable zone, yet neither supports life as far as we know. Venus became too hot due to atmospheric changes. Mars lost much of its atmosphere and surface water. This shows that simply being at the correct distance does not guarantee stability. Planetary atmosphere, composition, and geological activity all play critical roles. Now consider the nature of the star itself. Our Sun is relatively stable. It produces energy at a steady rate and has done so for billions of years. Some stars, however, are highly variable. Red dwarf stars, which are the most common type in the universe, often produce intense stellar flares. These flares release bursts of radiation that could strip atmospheres from nearby planets. Since red dwarfs are smaller and cooler, their habitable zones are very close to the star. This means planets in those zones are more exposed to radiation and tidal locking. Tidal locking occurs when one side of a planet always faces its star, while the other side remains in perpetual darkness. This creates extreme temperature differences between the two sides. It is uncertain whether such planets could maintain stable climates suitable for complex life. Stability becomes more fragile under these conditions. Another factor is planetary mass. A planet must be large enough to retain an atmosphere through gravity. If it is too small, like Mars, its gravity may be insufficient to hold on to thick atmospheric gases over billions of years. Why? Without an atmosphere, surface water evaporates or freezes, and protection from harmful radiation disappears. On the other hand, if a planet is too massive, it may accumulate thick layers of hydrogen and helium, becoming a gas giant with no solid surface. Earth's mass appears to fall within a narrow range that allows both a stable atmosphere and a solid surface. This balance contributes significantly to long-term habitability. The presence of a magnetic field is another crucial component of stability. Earth's magnetic field shields us from charged particles emitted by the sun. Without this protection, solar wind could gradually strip away the atmosphere, as likely happened on Mars. The magnetic field is generated by Earth's molten iron core and its rotation. This means a planet must not only have the right composition, but also sufficient internal heat and rotational characteristics to sustain such a field. Geological activity also contributes to stability. Earth's plate tectonics regulate carbon dioxide levels through a long-term carbon cycle. Volcanic activity releases gases into the atmosphere, while weathering and subduction recycle carbon into the planet's interior. This process acts as a thermostat, helping to stabilize global temperatures over millions of years. Without such regulation, a planet could drift into extreme greenhouse or icehouse states permanently. Interestingly, we do not yet know how common plate tectonics are among rocky planets. It may require a specific combination of internal heat, water presence, and crust thickness. If plate tectonics are rare, then long-term climate stability may also be rare. The moon plays an often overlooked role in Earth's stability. Our moon is unusually large relative to Earth's size. It stabilizes Earth's axial tilt, preventing extreme variations over time. Without the moon, Earth's tilt could shift dramatically, causing chaotic climate swings. The moon also contributes to ocean tides, which may have influenced early biological processes. The formation of such a large moon likely required a specific type of collision early in Earth's history, a massive impact with a Mars-sized body. This event was catastrophic yet ultimately beneficial. But how common are such collisions that result in stable moons rather than total planetary destruction? We do not know. The event that formed our moon may have been rare. Another aspect of stable conditions is chemical composition. Life as we know it depends on elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These elements were forged in earlier generations of stars. This means that planets capable of supporting life must form in regions enriched by previous stellar explosions. Very early in the universe's history, heavy elements were scarce. Only after multiple cycles of star formation and supernovae did enough heavy elements accumulate to form rocky planets. This suggests that the window for life-supporting conditions may have opened only after billions of years of cosmic evolution. Even then, the distribution of heavy elements varies across galaxies. Some regions may lack sufficient materials to build Earth-like worlds. Stability also depends on protection from frequent catastrophic events. Large asteroid impacts can cause mass extinctions. Earth has experienced several, including the one that likely wiped out the dinosaurs. Yet despite these events, life persisted. Too many catastrophic impacts, however, could prevent complex life from evolving at all. A planetary system's architecture influences impact frequency. For example, Jupiter's massive gravity may help deflect or capture some comets and asteroids that would otherwise threaten Earth. This protective role of gas giants may not exist in every planetary system. Some systems may lack such shielding, while others may experience chaotic gravitational interactions that destabilize orbits. Time is perhaps the most critical component of stable conditions. Intelligent life on Earth required billions of years of relatively stable climate and environmental conditions. Even small fluctuations can delay or reverse evolutionary progress. If Earth had experienced constant extreme volcanic activity, repeated sterilizing impacts, or prolonged global freezing, intelligent life might never have appeared. When we step back and list all these factors, correct distance from a stable star, appropriate planetary mass, magnetic field, plate tectonics, a stabilizing moon, protective gas giants, chemical richness, and long-term freedom from catastrophic disruptions, the number of required conditions becomes striking. Each factor may have a probability attached to it. When multiple probabilities multiply together, the final likelihood can become very small. For example, if each necessary condition had a 1 in 10 chance of occurring, and 10 such conditions were required, the combined probability would be 1 in 10 billion. This is a simplified illustration, but it demonstrates how complexity reduces likelihood. The rarity of stable conditions does not mean Earth is miraculous in a supernatural sense. It means Earth may represent a fortunate convergence of many independent factors. In a vast universe, such convergences can happen, but they may not happen often. This line of reasoning challenges the assumption that life is common simply because planets are common. The discovery of thousands of exoplanets has expanded our understanding of planetary diversity. Many systems look very different from ours. Some have giant planets orbiting extremely close to their stars. Others have eccentric orbits that would produce severe climate swings on any rocky worlds within them. While some exoplanets appear promising, we have yet to confirm one that matches Earth's full range of stabilizing characteristics. And even if we find Earth-like planets, we must still ask whether they remain stable over billions of years. Stability is not a snapshot. It is a long-duration process. A planet might appear habitable today, but may have been unstable for most of its history. Intelligence requires time, vast amounts of it. Without prolonged stability, evolution cannot experiment, diversify, and eventually produce complex organisms capable of thought and technology. When we continue examining the rarity of stable conditions, we must look even deeper into the chain of delicate balances that allowed intelligent life to emerge on Earth. It is not enough for a planet to briefly support water or maintain a mild climate for a few million years. Intelligence requires extraordinary patience from nature. It demands billions of years of sustained stability, resilience through catastrophe, and a sequence of fortunate transitions that may not commonly occur. Let us consider climate stability more closely. Earth's climate has fluctuated over time, but it has remained within boundaries that allowed liquid water to persist. This is not guaranteed on every planet in the habitable zone. Climate systems are complex and sensitive to feedback loops. A small increase in greenhouse gases can trigger runaway warming. A slight decrease can cause global freezing. Venus likely experienced runaway heating, while Mars may have lost atmospheric thickness and cooled permanently. Earth avoided both extremes. Why? Part of the answer lies in the carbon-silicate cycle, a long-term geological process that regulates carbon dioxide levels. Rain dissolves carbon dioxide from the atmosphere, forming carbonic acid, which reacts with rocks and eventually lock carbon into minerals. Through plate tectonics and volcanic activity, this carbon can later be released back into the atmosphere. This cycle stabilizes temperature over geological timescales. If a planet lacks active plate tectonics, this thermostat may not function. Without it, climate drift could make the planet permanently uninhabitable. Yet we do not know how common plate tectonics are. Some models suggest they may be rare among rocky planets. If that is true, then long-term climate regulation may also be rare. Another subtle but crucial factor is planetary rotation. Earth rotates once every 24 hours. This rotation distributes heat relatively evenly around the globe. If a planet rotates too slowly, extreme temperature differences can occur between day and night sides. If it rotates too quickly, atmospheric circulation patterns may become chaotic. The balance we experience on Earth contributes to moderate climate zones and biodiversity. Axial tilt also plays an important role. Earth's tilt of about 23.5 degrees creates seasons, which influence ecological diversity. However, if the tilt were highly unstable, swinging dramatically over time, climates could become unpredictable and hostile to complex ecosystems. Our moon helps stabilize Earth's tilt, reducing chaotic variations. Without it, simulations suggest Earth's axis might shift wildly over millions of years. Now consider stellar stability over time. The sun gradually increases in brightness as it ages. Earth's climate system has compensated for this slow increase for billions of years. But if the sun's luminosity changed too rapidly, life would struggle to adapt. Some stars vary unpredictably or emit powerful bursts of radiation. Such variability can erode atmospheres and damage biological molecules. Radiation is another often underestimated threat. Cosmic rays, solar flares, and nearby supernova explodes. Ions can flood planets with high-energy particles. Earth is partially protected by its magnetic field and atmosphere, but a sufficiently close supernova could still cause mass extinction. In denser regions of galaxies where stars are packed tightly, such events would occur more frequently. Our location in the Milky Way appears relatively calm, not too close to the crowded galactic center, not too far out in the sparse edges. This just right galactic position adds another layer of rarity. If a planetary system forms too near the center of a galaxy, gravitational disturbances and radiation levels increase. Too far away, and there may not be enough heavy elements to form rocky planets at all. Earth's location may fall within a narrow galactic habitable zone. Then there is the matter of water delivery. Some theories suggest that early Earth may not have formed with all its water. Instead, icy asteroids or comets may have delivered it during a period known as the Late Heavy Bombardment. This means Earth's water supply might depend on specific early solar system dynamics. Too much bombardment, and life would be repeatedly sterilized. Too little, and oceans might never form. Furthermore, life's chemistry depends on stability at the molecular level. DNA, proteins, and cell membranes require relatively narrow temperature ranges. They also require chemical environments that are neither too acidic nor too alkaline. Planetary oceans must maintain balanced pH levels. Even small long-term shifts could destabilize biological systems. We must also consider oxygen. For much of Earth's early history, oxygen was scarce. The Great Oxygenation Event, triggered by photosynthetic microbes, transformed the atmosphere around 2.4 billion years ago. Oxygen enabled the evolution of complex multicellular life, but also caused mass extinctions of organisms adapted to oxygen-free conditions. This transition required a delicate balance between biological innovation and environmental tolerance. If oxygen levels rise too high, wildfires become more frequent. If they fall too low, complex animals cannot survive. Earth's atmosphere has fluctuated within limits that allowed complexity but avoided permanent collapse. Another remarkable factor is planetary longevity. Earth has maintained liquid water for over 4 billion years. Many planets may begin with habitable conditions, but lose them due to atmospheric escape, orbital changes, or internal cooling. Mars may once have had rivers and lakes, but it lost its magnetic field and atmosphere. Its window of habitability may have been brief. Intelligence requires not just life, but complex life, and complex life took nearly 4 billion years to emerge on Earth. That means stable conditions must persist for extraordinarily long durations. If habitable periods typically last only a few 100 million years elsewhere, that may not be sufficient. Catastrophic events also test stability. Earth has experienced 5 major mass extinctions. Each time a significant portion of life vanished, yet life recovered. But what if one extinction had been slightly more severe? What if oxygen-producing organisms had been wiped out early? What if multicellular organisms never regained dominance? Stability is not the absence of disturbance. It is the ability to recover from disturbance. Earth's biosphere has shown resilience. Whether that resilience is common remains unknown. Even the arrangement of planets in our solar system may be unusually stable. Some exoplanet systems contain hot Jupiters, massive gas giants orbiting extremely close to their stars. Their migrations may disrupt inner rocky planets, ejecting them from the system or causing violent collisions. Our solar system appears comparatively orderly, with nearly circular orbits and long-term gravitational stability. The more exoplanets we discover, the more diversity we see. Some systems are chaotic, with planets in highly eccentric orbits. Others contain tightly packed configurations that would likely destabilize over time. Our solar system's relatively calm architecture may not be typical. All of these factors combine multiplicatively: stable star behavior, correct orbital distance, suitable planetary mass, magnetic shielding, plate tectonics, moon-induced axial stability, galactic positioning, balanced atmospheric chemistry, long-term climate regulation, protection from excessive catastrophic impacts, recovery capacity after extinction events. Each factor alone might not be extremely rare, but together, their combined probability may shrink dramatically. This perspective does not assert certainty. It does not claim Earth is uniquely miraculous. Instead, it emphasizes uncertainty about frequency. We have only one confirmed example of life-bearing stability, Earth. With a sample size of 1, we cannot confidently estimate how common such conditions are. Optimists argue that because the universe is vast, even rare conditions will occur frequently somewhere. That may be true, but rarity still matters. If only 1 in a billion planets achieves long-term stability, then even a galaxy with hundreds of billions of stars may host only a handful of suitable worlds. And then we must still consider the next step, the emergence of life and intelligence. Stable conditions are only the foundation. Without them, intelligence is still not guaranteed. The rarity of stable conditions challenges the assumption that life is inevitable wherever planets exist. It suggests that the path to intelligence may require a narrow corridor of physical and environmental balance. A slight shift in any direction, too hot, too cold, too chaotic, too unstable, may close that corridor permanently. When we reflect on Earth's history, we see not inevitability, but contingency. Our planet balanced on the edge of extremes many times. It avoided permanent runaway heating, It avoided total atmospheric loss. It recovered from devastating impacts. It sustained chemical cycles over billions of years. Such sustained balance may be one of the rarest achievements in the cosmos. If that is true, then intelligent life is not simply a matter of counting planets. It becomes a matter of identifying worlds that maintain fragile equilibrium across cosmic timescales. And until we observe many such examples, we must remain open to the possibility that stable conditions, the quiet, persistent stage upon which evolution performs, may be extraordinarily uncommon in the vast universe. The more we examine Earth's history, the more we see how close it came to disaster multiple times. Ice ages nearly covered the planet entirely. Volcanic eruptions altered atmospheric chemistry. Asteroid impacts reshaped ecosystems. Yet somehow, stability returned each time. This resilience may be rare. In conclusion, when we analyze the rarity of stable conditions, we begin to see that habitability is not a simple checklist. It is a delicate interplay of astronomical, geological, chemical, and temporal factors. Each must align not just briefly, but persistently. The universe may contain billions of planets, but how many maintain this intricate balance for billions of years? That remains unknown. And until we know, we must seriously consider the possibility that such stability, the K, ind required for intelligent life, may be far rarer than the sheer number of stars would suggest. When we examine why intelligent life may be unlikely, we eventually arrive at one of the deepest mysteries in science, the origin of life itself. Before evolution, before complexity, before intelligence, there had to be a first step. Non-living chemistry had to cross a boundary and become self-replicating, adaptive, and capable of evolution. That transition may have been extraordinarily fragile. Life did not begin with animals or plants. It began with chemistry. Early Earth was a world of oceans, volcanic activity, lightning, ultraviolet radiation, and a mixture of simple molecules such as water, methane, ammonia, carbon dioxide, and nitrogen. Under the right conditions, these molecules can form more complex organic compounds. Laboratory experiments have shown that amino acids, the building blocks of proteins, can form naturally under certain simulated early Earth conditions. But forming amino acids is not the same as forming life. Life requires organized systems. It requires molecules that can store information, copy themselves, and interact within protective boundaries like cell membranes. DNA and RNA are incredibly complex molecules capable of storing genetic instructions. Proteins perform specialized tasks. Cells regulate internal chemistry while separating themselves from the outside world. How did such an organized system emerge from random chemical reactions? This is where fragility becomes crucial. The early steps toward life may have required an extremely specific sequence of conditions: the right temperature range, the right chemical concentrations, the presence of energy sources, but not so much energy that molecules were constantly destroyed. Perhaps life began near deep-sea hydrothermal vents, where mineral-rich water provided catalytic surfaces, or P. Perhaps in shallow tidal pools where cycles of drying and wetting helped molecules bond together. We do not yet know the exact pathway. That uncertainty itself is important. It suggests that the origin of life is not a simple automatic consequences of having water and carbon. It may depend on rare chemical coincidences. Consider the concept of self-replication. A molecule capable of copying itself must be both stable and flexible. Too stable and it cannot change or evolve. Too unstable and it falls apart before replication. That balance is delicate. The first replicating molecules may have been easily destroyed by radiation, heat, or chemical disruption. If early Earth had been slightly more violent, with more asteroid impacts or stronger solar radiation, these fragile systems might never have survived long enough to evolve. Another layer of fragility lies in probability. Even if organic molecules form frequently, assembling them into a functioning, self-sustaining network may be extremely improbable. Think of it like shuffling letters randomly and hoping they form a meaningful sentence. With enough attempts, it might happen, but the number of attempts required could be enormous. Some scientists argue that, given enough time, life is almost inevitable. Others suggest that the jump from chemistry to biology may be one of the rarest events in the universe. If it required a highly specific and unlikely chain of reactions, then even billions of planets might not guarantee frequent success. We also must remember that Earth formed about 4.5 billion years ago, but life appears to have emerged relatively quickly in geological terms, perhaps within a few 100 million years. Some interpret this as evidence that life forms easily, but there is another interpretation. If life had not emerged early, it might never have emerged at all. Early Earth still had abundant shade, Michael energy, and dynamic environments. Later, conditions may have become less favorable. In this view, life's early appearance does not prove ease. It may reflect the narrow window of opportunity. The fragility of life's origins also raises another sobering thought. Even if simple life begins, it may not persist. Early life on Earth survived massive asteroid bombardments and dramatic climate shifts. If one of those events had been slightly more severe, it might have sterilized the planet completely. A single catastrophic event at the wrong time could erase all progress. When we consider the origin of life, we are not just asking whether chemistry can become biology. We are asking whether that transformation can occur, survive, and stabilize long enough to begin evolution. Each stage is vulnerable. Each stage can fail. Until we understand precisely how life began on Earth, we cannot confidently estimate how common it is elsewhere. The fragility of life's origins remains one of the strongest reasons to question the assumption that intelligent life is widespread. If the first spark of life required a rare convergence of conditions, then intelligence, which depends entirely on that first fragile step, may be even rarer than we imagine. One of the most common assumptions people make is that evolution naturally leads toward intelligence. We tend to look at human beings with language, technology, science, and self-awareness and imagine that evolution was somehow aiming for this outcome all along. But this idea misunderstands how evolution works. Intelligence is not the goal of evolution. In fact, evolution has no goal at all. Evolution by natural selection is a blind process. It does not plan, predict, or strive toward complexity. It simply favors traits that improve survival and reproduction in a particular environment. If a characteristic helps an organism leave more offspring, it becomes more common over time. If it does not, it disappears. That is the entire mechanism. For most of Earth's history, life was simple. Single-cell organisms dominated the planet for billions of years. Even after multicellular life appeared, complexity increased slowly. Dinosaurs ruled the Earth for over 150 million years, yet none developed advanced technological intelligence. They were highly successful in evolutionary terms. They survived, reproduced, and adapted to their environments. Intelligence beyond basic problem solving was not necessary for their dominance. This reveals something important. Evolution rewards adequacy, not superiority. An organism does not need to be the smartest possible creature. It only needs to be well suited to its ecological niche. Sharks have existed for over 400 million years with relatively little structural change. They are not technological, but they are extraordinarily efficient predators. Bacteria are even more successful. They thrive in extreme environments, reproduce rapidly, and exist in unimaginable numbers. From an evolutionary perspective, bacteria are among the most successful life forms on Earth. If intelligence were the inevitable outcome of evolution, we might expect it to have emerged multiple times independently. Yet on Earth, technological intelligence has appeared only once, in humans. Other animals, such as dolphins, elephants, and certain birds, show impressive cognitive abilities, but none have developed complex technology, advanced mathematics, or space travel. This suggests that high-level intelligence is not an automatic endpoint of evolution. Moreover, intelligence carries costs. Large brains require enormous amounts of energy. The human brain consumes a significant portion of the body's energy, despite making up a small percentage of its mass. Developing and maintaining such a BRR AIM demands stable food supplies and complex social structures. If environmental conditions are harsh or unpredictable, simpler survival strategies may be more efficient. Intelligence can also introduce risks. Self-aware species can alter their environments dramatically. They can overexploit resources, create destructive technologies, or destabilize ecosystems. In this sense, intelligence may not even be evolutionarily stable in the long term. A species capable of advanced technology may also be capable of self-destruction. Another critical point is contingency. Evolution depends heavily on chance events. The asteroid impact that wiped out the dinosaurs 66 million years ago cleared ecological space for mammals to diversify. If that asteroid had missed Earth, mammals might have remained small and insignificant. Humans might never have evolved. Our existence may depend on a sequence of highly improbable events. This highlights a deeper truth. Evolution does not move in a straight line toward complexity. It branches. It experiments. It produces diversity, not direction. Some branches lead to greater complexity. Others remain simple or even revert to simpler forms. Parasitic organisms, for example, often lose complex structures because they are unnecessary for survival in a host environment. Even within primates, human-level intelligence was not guaranteed. For millions of years, our ancestors coexisted with other hominin species. Many went extinct. Our survival may have depended on subtle environmental pressures, social cooperation, and random genetic variations. If a few small events had unfolded differently, modern humans might not exist. When we project this understanding onto the universe, the implications are profound. Even if life arises frequently on other planets, there is no guarantee it will evolve intelligence. It may remain microbial. It may develop into plants or simple animals. Intelligence requires specific pressures and opportunities, such as complex social interaction, environmental challenges that reward problem solving, and physical structures capable of supporting large brains. But even these factors do not ensure technological civilization. Intelligence sufficient for survival does not automatically lead to science or engineering. Cultural evolution plays a major role in human development. Language, cooperation, and accumulated knowledge allowed us to progress. These may depend on additional rare conditions. The idea that intelligence is not evolution's goal challenges human-centered thinking. We are not the predetermined outcome of nature's design. We are one possible result among countless alternatives. Evolution does not favor intelligence universally. It favors whatever works. This perspective forces us to reconsider assumptions about extraterrestrial life. Even if stable planets with life are common, intelligent civilizations may still be rare. The path from simple cells to conscious technological beings is not straight or guaranteed. It may require an extraordinary combination of environmental stability, biological innovation, and fortunate accidents. In the end, intelligence may not be the climax of evolution. It may be an unusual side branch, a rare experiment in the long history of life. And if that is true on Earth, it may be true throughout the universe. One of the most compelling reasons to question the prevalence of intelligent life in the universe is a puzzle known as the Fermi Paradox. Named after the physicist Enrico Fermi, it asks a simple but profound question. If intelligent civilizations are common in the galaxy, why have we seen no evidence of them? Given the vast number of stars and planets, one might expect the galaxy to be teeming with life capable of communication or interest, travel. Yet the observable universe is silent. To understand the paradox, it helps to consider some numbers. Our Milky Way galaxy contains roughly 100 to 400 billion stars. A significant fraction of these stars likely host planets. If even a tiny percentage of these planets are capable of supporting life, that could still represent billions of potentially habitable worlds. Over billions of years, some of these worlds should have developed intelligent life. If even a fraction of those civilizations became technologically advanced, capable of sending signals or exploring space, we would expect to detect them. And yet, despite decades of searching, we have found no conclusive evidence. Projects like SETI, Search for Extraterrestrial Intelligence, have scanned the skies for radio signals and other forms of communication. Astronomers have observed countless stars for signs of unusual energy emissions that might indicate large-scale engineering or industrial activity. So far, nothing definitive has been detected. The galaxy appears silent. This silence is striking, especially when contrasted with the age of the galaxy. The Milky Way is about 13.6 billion years old. Complex life on Earth emerged relatively late, in the last few 100 million years. Even if intelligent life arises slowly, the galaxy has existed long enough for civilizations to emerge, develop technology, and potentially expand across vast distances. If advanced civilizations were common, some of them might have colonized large regions of space or left detectable traces, yet none have. Several explanations have been proposed for this paradox. One possibility is that intelligent life is extremely rare. While simple life might arise frequently, the transition to complex technological civilizations may be extraordinarily unlikely. This idea aligns with other key points: the rarity of stable planetary conditions, the fragility of life's origins, and the fact that intelligence is not an inevitable outcome of evolution. Taken together, these factors could make civilizations exceedingly uncommon. Another possibility is that intelligent civilizations tend to self-destruct. Advanced technology can bring existential risks, such as nuclear warfare, environmental collapse, or uncontrolled artificial intelligence. If civilizations frequently destroy themselves shortly after reaching technological maturity, the galaxy might be populated by transient civilizations whose signals are too brief to detect. The third explanation considers distance and time. The galaxy is vast, and communication or travel may be limited by physical constraints. Even if civilizations exist, they may be too far apart to detect one another. Signals take years, centuries, or millennia to travel, and civilizations may not overlap in time. One civilization could rise and fall before another even becomes aware of its existence. Another intriguing possibility is that advanced civilizations deliberately avoid detection. Perhaps they recognize the dangers of interstellar contact or prefer to remain hidden. Some theorists call this the zoo hypothesis, suggesting that intelligent life may observe us from afar without interfering, much like humans study wildlife in a preserve. Some explanations explore the limitations of our own detection methods. Perhaps civilizations communicate in ways we do not yet understand. Radio waves are just one narrow method of transmission. Advanced beings may use technologies beyond our comprehension, making their signals effectively invisible to us. Despite these possibilities, the Fermi Paradox underscores a critical point. The absence of evidence is itself evidence of rarity or difficulty. In a galaxy of billions of stars and planets, the continued silence suggests that intelligent life may not be widespread. The paradox does not prove that we are alone, but it forces us to confront the possibility that technological civilizations like ours are exceptionally rare. The paradox also challenges anthropocentric assumptions. Humans often assume that intelligence and technology are inevitable endpoints of evolution. Fermi's question reminds us that even on a planet where life exists, there is no guarantee that intelligence will emerge or survive long enough to become detectable. The universe may be full of life, yet almost entirely microbial, with complex life and civilizations as outliers rather than norms. Ultimately, the Fermi paradox combines empirical observation with logical reasoning. It asks us to reconcile the vastness of the cosmos with the absence of contact. Whether the answer lies in rarity, self-destruction, cosmic distances, or hidden civilizations, the paradox illustrates the profound uncertainty surrounding intelligent life. It suggests that our existence and our ability to contemplate the universe may be a rare phenomenon, perhaps one of the few sparks of consciousness in a largely silent cosmos. The paradox does not diminish humanity's significance. Instead, it highlights the unique opportunity and responsibility we have as a potentially rare intelligent species. Our civilization may be among the first or few capable of understanding the universe. The silence of the cosmos reminds us to value knowledge, exploration, and preservation, because if intelligent life is rare, the survival of our own species could carry profound cosmic importance. One of the most important lessons in evaluating the likelihood of intelligent life comes not from astronomy or biology, but from the approach of a single remarkable scientist, Richard Feynman. Feynman was renowned not only for his contributions to physics, but also for his philosophy of inquiry. He emphasized intellectual honesty, skepticism, and the need to base conclusions on evidence rather than assumptions or wishful thinking. When applied to questions about extraterrestrial life, his perspective provides a framework for understanding why the universe's apparent emptiness may not be surprising. Feynman's skepticism was rooted in careful observation and rigorous reasoning. He often warned against the human tendency to see patterns where none exist or to assume outcomes because they feel intuitively correct. In the context of intelligent life, this means we should not assume that life must exist elsewhere simply because the universe is vast. The size of the universe is indeed impressive, but as Feynman might argue, vast numbers alone are not proof of likelihood. Probability, contingency, and complex interactions must all be considered. One of Feynman's key ideas was the distinction between imagination and evidence. It is easy to imagine a universe teeming with civilizations, with countless planets hosting life, and advanced societies communicating across galaxies. This vision is appealing and even comforting, yet Feynman would caution us: imagination is not evidence. Scientific reasoning requires that we test hypotheses and rely on observable phenomena. Currently, we have no confirmed evidence of extraterrestrial intelligence. Our observations, the silence of the cosmos, the absence of detectable signals, the lack of visible artifacts, are concrete facts. Feynman's approach would be to let those facts guide conclusions rather than hope or expectation. Feynman also stressed the importance of understanding the limits of our knowledge. He famously said, "I can live with doubt and uncertainty and not knowing." I think it's much more interesting to live not knowing than to have answers which might be wrong. In terms of life beyond Earth, this principle reminds us that the apparent rarity or absence of intelligent life in our observations does not prove that life is impossible. It simply highlights the uncertainty inherent in the problem. We have only one confirmed example of intelligent life, ourselves, which makes extrapolation inherently speculative. Feynman's skepticism encourages humility. We cannot assume we understand the full range of possibilities. Another aspect of Feynman's philosophy was recognizing complexity. Life is not a simple, predictable outcome. Evolution does not aim for intelligence. Planetary conditions are not automatically stable. Chemical processes leading to life are fragile. Feynman's approach emphasizes that such complexity resists simplistic assumptions. When examining the likelihood of intelligent civilizations, it is not sufficient to multiply stars by planets and assume that life must be common. Each step in the chain, planetary formation, stable conditions, origin of life, evolution of complex organisms, development of intelligence, and survival of civilizations, is uncertain and potentially rare. Feynman's method would have us calculate probabilities carefully, acknowledging each uncertainty rather than glossing over it with intuition. Feynman also championed critical thinking and the willingness to revise beliefs. If new evidence emerges, for example, the detection of microbial life on Mars or signals from another star system, our understanding must change. Scientific skepticism is not cynicism, it is an openness to correction and refinement. In the search for extraterrestrial life, Feynman's mindset encourages ongoing investigation while avoiding premature conclusions based on wishful thinking. Applied broadly, Feynman's skepticism explains why the absence of evidence can be as meaningful as the presence of evidence. The Fermi Paradox, the contradiction between the high probability estimates of extraterrestrial life and the lack of observed contact, illustrates this principle. Feynman would urge us to take the paradox seriously, to question assumptions, and to consider that our expectations may reflect human biases rather than cosmic reality. Ultimately, Richard Feynman's approach to scientific inquiry is a guide for navigating uncertainty. When evaluating the probability of intelligent life, we must combine humility with rigorous reasoning. The vastness of the universe, the fragility of life, and the contingency of evolution all require careful evidence-based analysis. Feynman's skepticism reminds us that extraordinary claims, such as the widespread existence of intelligent civilizations, demand extraordinary evidence. Until that evidence emerges, caution and rigorous inquiry remain our most reliable tools. In this way, Feynman's philosophy shapes the broader discussion about life in the cosmos. It encourages curiosity without illusion, observation without assumption, and logic without preconception. His approach teaches that the universe is a place of immense complexity and uncertainty, and that our conclusions must reflect that reality. In considering why intelligent life may be unlikely, Feynman's skepticism serves as both a warning and a framework to look carefully, think critically, and respect the limits of what we truly know. Richard Feynman, one of the most brilliant physicists of the 20th century, was not only known for his groundbreaking work in quantum mechanics and particle physics, but also for his philosophy of inquiry and skepticism. His approach to science provides an essential lens through which we can examine the question of intelligent life in the universe. Unlike popular speculations about extraterrestrial civilizations, Feynman's perspective emphasizes observatio,